Alright guys, Mr. Antonucci here, and in this video we want to talk about exponential and logarithmic functions. And first thing we're going to do is define what exponential functions are and use their properties. So in general, an exponential function, an exponential function involves a positive constant a raised to a power where a is not equal to 1. It's written as f of x equals a to the x. And the reason we exclude 1 is if you had 1 to the x power, that's equal to 1, which is the constant function y equals 1. So let's look at some properties of exponents. Let a and b be any real numbers, x and y be any real numbers also, then the following properties are true. This one, a to the 0 power is 1. Any constant raised to the 0 power is equal to 1. The second one is often referred to as the product property. When you multiply like bases, you add the exponents. This is the power property. When you have a power to a power, you multiply the exponents. This is the product to a power property. It just says when you have two bases being multiplied together to a power, you can kind of distribute the power there. This is the quotient property. When you divide like bases, you subtract the exponents. This should be a to the y power. The only way that works is if the bases are the same. This one here is the quotient to a power. Basically, if you have a fraction to a power, you can raise the numerator and denominator to the same power. And this is the property for negative exponents, and it works both directions. So if you have a to the negative x, you could rewrite it as 1 over a to the x. Or if you have 1 over a to the x, you could rewrite it as a to the negative x. Now we're going to use the properties here to simplify these expressions. So this one is just going to be 2 to the 5th, because when you multiply like bases, you add the exponents. This one here is going to be 2 to the negative 1. When you divide like bases, you subtract the exponents, and you could rewrite this as 1 over 2 to the first power, or just 1/2. 3x to the third. This is the power property where you multiply exponents. So this would be 3 to the 3x. And this last one here, there's a couple ways we could do this. We could first rewrite 1/3 as 3 to the negative 1 to the negative x. And then you have a power on a power, and you multiply those, you get 3 to the positive x. The other way we could do it is if you had 1/3 to the negative x, that's a quotient to a power, you could do 1 to the negative x over 3 to the negative x. And that would flip over and give you 3 to the x over 1 to the x. And 1 to the x is always 1. Or you could reverse the property and write it as 3 over 1 to the x, which is just 3 to the x. But I think this way is much more simple. Okay, next thing we want to look at is graphing and comparing exponential functions. So we're going to go in Desmos and we're going to graph each of these three functions and look at some of their similarities and some of their differences. But one thing I want to look at before we do that is this 1/2 to the x. You could rewrite it just like we did in part D up here as 2 to the negative 1 to the x, which is 2 to the negative x. Might be a little bit easier to graph that one there. Okay, so here we are. We have the three functions. Let's look at them one at a time. 2 to the x, notice it's increasing and has a y-intercept of 0, 1. The second one, notice now it's decreasing, and the only difference is that the exponent is negative, which reflects the function 2 to the x over the y-axis. It's also decreasing, and the y-intercept is still 0, 1. The third function, 3 to the x, is increasing. It's in green here. And let's compare it to the red one. Notice that it's increasing at a faster rate than 2 to the x is, but it also still has the y-intercept 0, 1. Another important thing to note about the shapes of exponential functions: if you have a positive base to a positive exponent, to a positive x, then the function's going to be increasing on its domain. If the exponent is negative for an exponential function, the function is going to be decreasing. And this is true if the base is greater than 1. Okay, so let's look at some properties of exponential functions. So if you have f of x is a to the x or g of x is a to the negative x, remember a is a real number and we're going to assume it's greater than 1. Just as a side, if you have a less than 1, that means it's going to be, you can think of it as a fraction like 1/4, and you could rewrite 1/4 as 4 to the negative 1. So if this was 1/4 to the x, you could rewrite this as 4 to the negative 1 to the x, which is 4 to the negative x. In other words, even if you do have a as a fraction, you could rewrite it as a base of a real number greater than 1, and then these properties would apply. The domain is all real numbers, negative infinity to infinity. The range is from 0 to infinity, all positive real numbers. The graphs have a y-intercept of 0, 1, and the functions are 1 to 1. That's very important because that's going to help us as we move forward with exponential functions. The next thing we want to talk about is the number e. Now I know e's a letter, but it represents an irrational number. The decimal approximation is right here, but since it's irrational, the number of the decimal places go on forever, and it never repeats, never ends. And as we proceed through this course, this number is going to be important for us, and it's going to become more apparent as we work through this. So in this example here, we want to describe the behavior of f of x equals 1 plus x raised to the 1 over x power at values close to 0. Now you might think this seems kind of random, but one of the reasons we want to look at this is because this function is undefined at x equals 0, because the exponent here you would be dividing by 0. So let's jump over to Desmos and check it out. So here I have the function, I have the graph of the function and the table, because we are interested in what happens as x gets close to 0. Now notice if I go right on 0, the function is undefined. If I put it in the table, it gives me undefined. But values close to 0, let's go negative 1, it's going to be undefined there. That's because if you plug negative 1 in, the base is going to be equal to 0. So if I go negative 0.5, negative 0.25, negative 0.1, negative 0.01, negative 0.001, negative 0.0001, 0.00001. And then if I look at values that are getting close to 0 from the right side, if I look at 1, 0.5, and what we realize is that the closer you get to 0, the closer these points get to the actual value of e to the x. So it may seem kind of random, like why do we just pick this function seemingly out of nowhere? But again, as we proceed through the course, it's going to become more apparent. So the next thing we want to do is graph the exponential function e to the x and identify its domain, range, intercepts, and whether it's increasing or decreasing. Okay, so here is e to the x. Since it's an exponential function, the base is e, which is greater than 1. The domain is going to be all real numbers. The range is from 0 to infinity, so all positive real numbers. The y-intercept is 0, 1. We can verify that by plugging 0 into the function and getting 1. And also the function is increasing on its entire domain, which also indicates that it is going to be a one-to-one function. So that's the graph of e to the x. All right, so the last thing we want to do is define the natural logarithmic function and use its properties. Now, like we just said, because the function e to the x is one-to-one, it must have an inverse function. So we define this function as the natural logarithmic function, and we write it ln of x. So this is the notation of it, and here's how it works. Natural log of x, say that's equal to some number, call it b. If and only if e to the b is equal to x. In other words, natural log is a function. If you take the natural log of a number, you get whatever the answer is. Since e to the x is the inverse of natural log, and natural log is the inverse, if you take e and raise it to that power of the answer that you just got, you should get back to the original number. So this is, in essence, how inverse functions work. We can rewrite logarithmic equations as exponential and exponential as logarithmic. And here's just some basic ideas. So one of the properties is that natural log of 1 is 0, and that's because e to the 0 is equal to 1, and vice versa. The natural log of e is going to be equal to 1, and that's because e to the first power is itself just e. And one other thing is that natural log of 1 over e is equal to -1, and that's because e to the -1 is equal to 1 over e. This is the inverse relationship between natural log and e to the x. So since natural log is defined as the inverse of e, their graphs are reflections of one another over the line y equals x, and we'll check that out in Desmos. So here in black I have the graph of e to the x, and in blue I have the graph of natural log x, and we can see that they are reflections of one another over the line y equals x. Also, look at the point of the y-intercept on e to the x. It's the point 0, 1. Well, the inverse point should swap the x and y. Well, if I look at the x-intercept of the natural log function, which would be the point reflected from the graph of e to the x, it's 1, 0. Notice the x and y are flip-flopped. And we can do this for any point on the graph. Any point over here is going to be reflected over here, and similarly on this side is going to be reflected on that side. So this brings us to some properties of the natural logarithmic function. If g of x is natural log x, the domain is from 0 to infinity, but the range is all real numbers, -infinity to infinity. The g-intercept, or the x-intercept of the graph, is 1, 0. There is no y-intercept. And this function is also 1 to 1. Now, since natural log and e to the x are inverses, you can compose them in either direction to undo one another. In other words, if I do g of f of x, which is natural log of e to the x, the natural log and the e undo one another and you get x. Or if I do f of g of x, then you would put natural log x in for the exponent of e to the x. The natural log and the e are going to cancel and you get just x. So we have some properties of logarithms, and these are a result from the properties of exponents. So if you have natural log of a product, you can add the natural log. One thing students sometimes mistakenly think is that if you have the log of a sum, that is not necessarily equal to natural log x plus natural log y. Okay, so don't make that mistake. The quotient property, if you have the log of a quotient, you can subtract the logs. And if you have log to a power, the power property says you can bring that in front as a product there. And these follow directly from the properties of exponents. So what we're going to do is expand each of these expressions here. So natural log of 10/9 is going to be natural log 10 minus natural log 9. And that follows from the quotient property. Now you could take this one step further, because 9 is a perfect square. You could rewrite this as natural log of 3 cubed, and then use the power property and do natural log 10 minus 3 natural log 3. This next one, since the square root, you can rewrite square roots as the 1/2 power. Then you could use the power property here and write it as 1/2 natural log of 3x plus 2. Now you can't go any further here because you can't break apart addition, and also the 1/2 cannot be distributed to the 3x plus 2 because the natural log is an operation. Here we could use the quotient property, so this would be natural log of 6x minus natural log of 5. And since we have a product here, we can rewrite that as natural log 6 plus natural log x, and then minus natural log 5. And then this last one is pretty crazy here. One of the first things we can do is notice that you have a quotient here. So this is going to be the natural log of x squared plus 3 quantity squared minus natural log of x times the cube root of x squared plus 1. Then this first one, the 2 can come down from the power property, 2 natural log of x squared plus 3 minus, here the cube root can be rewritten as the exponent 1/3. But we have to be careful here because there is a product. Now that product we can rewrite as the sum of logs, but we have to be careful because of this subtraction here. So I'm going to put that in parentheses, natural log of x plus natural log of x squared plus 1. Now I would write 1/3 power there, but I can bring that down front as the coefficient. Now the last thing we can do is distribute that negative. So this is our final answer here. Now I wrote f of x equals natural log of x squared here because this introduces an important point about logarithms. When you rewrite the natural logarithmic function using these properties, you have to check to see that the domain of the rewritten function is the same as the original function. So for this one, we can do the natural log of x squared. The domain is going to be all real numbers for x not equal to 0. Because when you square a negative, you get a positive. And natural log's defined for all positive values, so the only thing that wouldn't work is x equals 0. But if I rewrite this using the power property, we have 2 natural log of x. Because the x is no longer squared, the domain for this is just going to be 0 to infinity. So here we have natural log of x squared in green. And if I bring the 2 down and write it as 2 natural log x in red, notice it only exists for the positive x-axis. Notice the original was all real numbers not equal to 0 is the domain. And this one is only positive numbers. Okay, so the last thing we want to do here is solve each equation. So in this case, the x is in the exponent for this first example. And how we would take care of that is first thing we would do is natural log both sides. So natural log e to the x plus 1. And the reason we do that is because the x is trapped in the exponent and natural log undoes the e. So you log both sides and you would have natural log of 7 equals x plus 1. And then x equals -1 plus natural log of 7. You could have written it as natural log of 7 minus 1, but be careful because that looks like the 7 and 1 could possibly be subtracted to get natural log 6. And the way you can avoid that is just put that 7 in parentheses or write the -1 in front there. Also, the decimal approximation to 3 decimal places would be 0.946. Last, we have natural log of 2x minus 3 equals 5. So in this case, the x is trapped inside the natural log, and we know that e undoes natural log. So what we do here is called exponentiate both sides. You just raise each side as a power of e. So e and the natural log cancel here, and you have 2x minus 3 equals e to the 5th. And then you just solve for x. So add 3. So e to the 5th plus 3. Make sure it's clear that the 3 is not adding the 5 in the exponent. And then divide both sides by 2. So you'd have e to the 5th plus 3 over 2. Or you could write that as 1/2 times e to the 5th plus 3. So 1/2 parentheses e to the 5th plus 3, and you get 75.706. Now, one thing you could do is take the one side that had the x in it in the original problem, so natural log of 2x minus 3, and then evaluate it at the 75.70657955513. And you could see that we ran out of decimal places of accuracy, and we were solving the equation for when it equals 5. So this would be the exact answer This is the decimal approximation, so be careful on what a question is asking for. All right, guys, that's it for this video. Hope that was helpful to you. As always, reach out if you have any questions, and take care.